So let me step you through the process of taking a curved set of experimental data and running it through a 6-step process to turn it into a line. And this is a relatively simple process, and for a set of data this size, it would probably only take you about 15 minutes to do. And so what we have is David Scalia holding a golf ball here, and we've got our expert behind the camera, Andrew Sheets. We're using a tripod to steady the frame, and we're using a very bright object falling against a very dark background that has markings on it so we can see our 10 centimeter marks. And I'm going to run this through Logger Pro to collect the data. So here's the video. And now here's the process of pulling the data from Logger Pro. And I've set up my axes to align with this. And what I'll do is, and you can watch in the background here, here's the graph that's going to be generated from the data. You can see the data points being generated as I click on them frame by frame as this ball drops. But as you can see, because this ball is so small and bright, my crosshairs of my cursor fit right over it, so I can get very accurate data. And you can see over here, these are the data table that's being created for me as I do that. So if I skip ahead here, so here's the data as it goes to the ground, and then what I do is I go through and look at the graph that's created. It plots a y position versus time, an x position versus time graph. The x position versus time is not moving in the x direction, it sits at 0 on the x-axis, and the y, it starts at 2 meters and drops down to 0 on the ground. And as you see, it's a very nice smooth curve. And I actually also run through a regression analysis using Logger Pro to see what the data looks like using 21st century methods rather than the method that they're probably going to ask you to do on the AP in an open response question. But the AP open response methodology is a nice methodology for a simple set of data, so it's worthwhile seeing how this process works. So let's move on and see what our result was from Logger Pro. And what we found in Logger Pro was that, first of all, you find that G equals 9.77 meters per second squared relative to 9.80. So we're only about 1/4% error on this data, which is a very close match. You don't get better experimental data than this in our high school lab. Secondly, the root mean square error, which we see here, is only 1.6 millimeters over a 2,000 millimeter drop, and so it's much less than 1% variance from our data, and so that's a very, very good fit. And so it's a nearly perfect fit for this model. And remember, what a regression does, it's a computer algorithm. Actually, you can do this algorithm by hand as well, that steps through to find a perfectly fitting function that matches our data to minimize the total root mean square error in the problem. And so you cannot find a better parabola to fit this data is what that means. And the advantage of this process using a regression is that every single one of our data points is used to help make this physics model that we came up with. And the physics model that we came up with is y equals negative 4.89 t squared minus 0.06 t plus 1.99 meters. And you can see we started at about 2 meters, and sure enough, there's our 2 meters. We started at 0 meter per second velocity, and you can see that's around 0. And there's our 1/2 of our acceleration. And so this is the method that I would prefer using on a lab if I had the option. But on the AP exam, we've got to use a different method. So here's this method. And you can see it's pretty easy. We've got, I don't know, about 20 data points or so. And so the first thing we're going to do is write down the model which theoretically we should find when we plot the data. And of course, we know where this comes from, so I won't go through that. But the problem with this formula is that there are 2 instances of our independent variable time showing up in our equation in 2 different terms. And that would be a bear to actually try to use this in this process, this 6-step process. And the 6-step process is basically doing a compression of your time scale to make it linear. And so we can actually, as it turns out for our problem, we're starting at 0 meters per second, so we can tweak this equation a little bit. And now we have a single independent nonlinear variable sitting right here, our t squared. And so we're going to use that to work out this process. And the next step in the process is simply to factor out this nonlinear independent variable out of this equation. Easily done because it's nearly done in any case, so I'm just going to do that. Here it is, factored out. Easy. And now, next step in the process, we're actually going to replace this time variable here as the independent variable that we'll graph for this variable t squared as our independent variable. And in calculus, we do this all the time. What we do is we take t squared and we'll do what we call a u substitution. And we'll have 1/2 ay times u plus y naught. And u would be our nice linear variable, just like having an x there for a line. So what we're going to do is we're going to add a new column for this new set of data. And we're going to take our t and we're going to replace it with t squared. And so here's our t squared. And then our next step is to recalculate this entire column using our time values, and we'll square each one to come up with a new set of independent values to run along our independent axis. And so I've squared each one of these, and here's the data for that. And what we'll do now is we'll go back to our original graph that we did, and if you've already on graph paper graphed the curve to find out that it's a curve, you can just rework your linearization process right on that same graph. We can use these same values on the time scale down here, except what we'll do is we're going to add a second independent axis, and that's going to be our new linearized variable t squared. And for this t squared axis, we're going to plot each one of these values against our heights. And let me show you how that works for a couple of points. For example, at time 0, or times when time squared is 0, our height is 1.99. So at 0, we're up at 1.99, and that's that point right there. And let me pick out another sample point over here. For example, at time squared equals 0.25, we should be at a height of 0.74. And so here we are at a time of 0.25, halfway between, this is time squared of 0.25, halfway between 0.2 and 0.3. And if I go up, you can see I've plotted this at 0.75 meters high. And so really, we're just creating another graph right on top of the other one using a newly revised independent variable called time squared rather than time. And you notice magically, this set of data of time squared versus height is perfectly linear. And that's what we were looking for. That's what we call our linearized data. So essentially, we've compressed on our time scale, we've compressed all these to a time squared scale. And because of the nature of our original starting function, that actually linearizes our data. So once we have that time squared value, step 5 is to just draw a line of best fit through that data and work out your equation for it. And so here's a line of best fit. I actually cheated and I used a regression because I had this in Excel. You're going to do this with a ruler, and you need to, as closely as possible, go through the center of all of your data. In this case, it's easy because we just go right through the data. And then you're going to go through, show a slope, use a slope triangle, and work out your slope and your y-intercept. My y-intercept, I would have picked out if I was doing this by hand, probably exactly 2. But you'll notice here that the r squared that I got when I ran it through Excel, they actually show as 1. As we mentioned before, an r squared of 1 means your data fits perfectly to the line. Chances are it's not actually 1.00000. Chances are it's like 99.993 or something like that, and it just rounds to 1. But as you can see, it's a very, very close fit. Same thing for our original parabola as well. That showed up as an r squared of 1. Finally, the last step in the process is to analyze what this means. And what we need to do is, let's write down our line of best fit. All right, here's the line of best fit we just developed. Then we're going to write down what our theoretical model is that we're basing this on. It's 1/2 ay t squared plus y naught. And what we see here is that 1/2 ay corresponds to negative 4.98. And then our y naught, our initial height, corresponds to 1.99, so it's our starting height. That was true. We started the ball at 2 meters. And so what we can do is we can actually use this to solve for ay. We can actually take the negative 4.98 and set it equal to 1/2 ay and solve for ay, and we get ay equals negative 9.96 meters per second squared. And that, when we compare it to our gravitational acceleration of negative 9.80 meters per squared, is about a 1.6% error. So we lost a little bit of precision running a line of best fit rather than a regression on our actual data. But even so, we're still within 2% error. Very good. And this is, like I said, this process, if you've already graphed your initial data, to run through and calculate another new column of data, plot it, draw a line through it, probably about 15 minutes worth of work for about 20 data points. On the AP exam, they probably only give you 6, 7, 8 data points, so it's actually faster than that. All right, let's try this again. Now, this time you have a set of data that I gave you. You've already graphed that and found out it's nonlinear. And what we did is we ran a little experiment, and actually I did this experiment last year and collected the data. We actually had a bare incandescent bulb that we lit up. And an incandescent bulb is the old style that has the filament inside that are very energy inefficient. But the nice thing about this is what we call a point source. All the light is emanating, roughly speaking, from one point inside of the bulb, and it radiates outward in all directions. And we took a light meter, which you see below, and the light meter measured the intensity of the light coming out in foot candles. All right, and those are US customary units. 1 foot candle equals 10.8 lux, and a lux, by the way, LX, as it's abbreviated, is 1 lumen per square meter. And as you can see, this is what we call a form of intensity. We're taking some sort of radiant energy here, or power. Lumens is actually a form of a radiance, and we're seeing how it spreads out over a uniform area. And so our units coming out of this should be converted into lumens per meter squared. And you should definitely do that on your data sheet that I gave you. If you've already graphed this, that's okay. You can just take the scale of your graph and convert each one of the scale numbers over to lumens per meter square instead, using these conversion factors. And so you don't have to regraph any of your data or recalculate any of your data. That's fine. So what we did is we took our meter and moved it away from the light 5 centimeters at a time and took a new reading for each distance. And then you graph the data. And your goal is to use this data to find the output of the bulb in lumens. And we're going to have to see if we can fit a model to that curve. We can actually calculate what this number of lumens will be, and then we can actually look up in a chart to see what type of light bulb provides that many of lumens, and you should be able to tell me the size of the light bulb I used. So this is what your graph looked like. Now remember, I gave you lumens and distance from bulb in centimeters, and really what we need to plot to do this in SI units is to plot the lumens per meter squared on this side, your lux. And then on this side, we should really change this to meters. And like I said, you've already probably graphed this, and all you need to do to convert this data is just to convert your scales down below. So right down below, you can just write down the values 0, 0.2, 0.4, 0.6, 0.8, and 1.0 in meters, and do a quick conversion from foot candles into lumens, and create a secondary axis, a scale over here, which shows you what the lumens per meter squared, or lux, units are. What is this shape? What apparent shape does it look like from your math class? And more importantly, why would it be that shape? And we can run through the laundry list of different shapes from the beginning of the lecture that we started here. We had a variety of types of shapes that you learned about in math, starting from probably back in 4th, 5th, 6th grade. Lines. All right, we have a proportional function, which goes to 0, straight line. Certainly this isn't that. We have any type of general linear function, which is any other type of line. It certainly isn't that still. We could look at parabolas. It's not a parabola because it doesn't curve up on this side. And a lot of people originally start thinking, okay, it's a parabola. It's not a parabola. It's not coming back up again. We don't have a big flat vertex on a parabola. All right. What about a cubic function or a 4th degree polynomial, and so on and so forth? No, those are a lot curvier. Then some people say, hey, this looks like maybe it's a natural log function or an exponential function. And it can't be either of those because of the way those functions pass through either the y-axis or the x-axis. So if you take a closer look at this function, you'll notice that it looks like we're asymptotic to the horizontal axis as well as the vertical axis, or sweeping up to both of those. And what types of functions do that? Well, rational polynomials do that. For example, hyperbolas, y equals 1 over x, or y equals 1 over x squared, y equals 1 over x cubed. That format of function. In fact, if you think about the units of intensity, They are actually, we have foot candles here, but if you think about the SI units, it's lux, or lumens per square meter, and down here we have meters. So if we have meters here and 1 over meters squared here, that gives you good indication that we have 1 over r squared type of units on this axis. So using a little bit of a clever dimensional analysis and looking at shapes that you know from mathematics, you can get a good idea of what this might be. But let's think about theoretical ways to show that this is what it is. All right, so what we have is our light bulb, and our light bulb is sending out beams of light in all directions. And I'm using 6 rays of light to represent all the light that's coming out in all directions. And I'm going to treat this sort of like the sun. Let's take a look at the sun. The sun's a point source in space, a very big point source, but if you compare it to all of space, it's very tiny. And we have Mercury, we have Venus, we have Earth, we have Mars a bit further out, and we have Jupiter. And this is roughly the scale of what we'd see our planets in order from the distance of the sun. Mercury is very close. Earth, Venus, and Mercury are split up in about thirds in here. Mars is a bit further out, about 1.4 distance relative to the Earth, and Jupiter is about 5 times the distance of the Earth out from the sun. And my question is, or we're going to look at this little model here. What if we were to take, and the people on Mercury were to build a hollow sphere capturing all the energy from the sun so they could keep it for themselves? So, and if we compare that to the folks on Venus, or on Earth, or on Mars, or on Jupiter, what would the difference be between each of these spheres? How do these spheres differ in terms of how they capture that light from the sun? All right, so we're going to ask some questions. By the way, these are a theoretical construct named by a technologist, famous technologist named Freeman Dyson, and we call these a Dyson sphere. He had this idea that aliens out in space might have built a sphere around their sun to capture that energy and use it and have more places to spread out and live. And some scientists more recently are saying, yeah, maybe he was right, but maybe he's not doing it around a sun the size of Earth, but maybe of Earth's sun, but maybe a small dwarf star or something. You could build a Dyson sphere that's much, much smaller in size and capture that energy and make it a habitable zone for their population. So this is not a, maybe it's a far-fetched idea, but who knows? Maybe some advanced alien civilizations have actually done this. So what we want to do is we want to look at this. I want to know how much light is captured by each of these Dyson spheres. A small one, larger, 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 larger by each one of these alien populations on these planets. Well, of course, the answer is they capture all of it in each case. And so 100% of the light is captured by each one of these. I'm looking for a relative answer, as it turns out. So in each case, we capture all of the sunlight. In that case, is there any difference between the experience somebody would have standing in one sphere on Mercury versus the sphere on Venus versus Earth, Mars, or on Jupiter, if you were able to do so? Well, sure, there's going to be a difference. And the big difference is that the amount of light is the same. However, the amount of area that's spread over is much larger for each different sphere that you have moving out at a further and further radius. So the intensity of the light, the amount of light that's spread out per unit area, it differs in each case. And in fact, if you want to get an idea qualitatively how that is, if you look between two of these beams, you can see on the Mercury sphere, we'd have this much, the amount of sunlight captured between here and here, about 1/6 of our sunlight, would be spread out over this small, very small area. So it would be very densely spread out onto that area. So it would be very hot. If you go over to Venus, that same amount of light, that same 1/6 of our light, is spread over this area, which is a much larger area than it is over here. And on Earth, it's even larger yet. And on Mars, that same amount of sunlight spread over a larger area yet. And on Jupiter, it's even a larger area yet. Now remember, this diagram that I have is drawn in 2 dimensions. We actually have to think in 3 dimensions. All right. So when we think in 3 dimensions, first of all, we've got to look at our intensity. Basic definition for any type of intensity, whether it's for light, for sound, or other radiant type of energy. We can also think about this for area, or for pressure, should I say. we've got, in this case, we've got the light that's being emitted by our light source, and we're going to divide it over the entire area of the sphere that we're on which we're sitting. We just divide these two, and we find out our units in this case are going to be lumens per meter squared. Of course, those are the units for lux. And so essentially, if you were on Earth, you're essentially taking a look at a sphere that's right around where the Earth is, and on the sphere, here we are on Earth, we're capturing a certain amount of the Earth's sunlight, and it's spread over evenly across this whole sphere a certain distance to give us our nice warm sunlight. On Venus, it'd be spread over a smaller area, it'd be much more intense, and you'd get sunburn in about 10 minutes versus 2 hours on Earth. And on Mercury, which is even closer, you would get sunburn in about 30 seconds, probably less. Versus on Jupiter, if you go out to Jupiter, that same sunlight spread over a much larger area, so the area is increasing, and you would take probably a year to get sunburned under the new sun. So let's start with the equation for the volume of a sphere, which is 4/3 pi r cubed. And it turns out in calculus, you calc folks can explain why this is. If you take the derivative of this function, you actually get the surface area of a sphere is 4 pi r squared. So this three-dimensional sphere has a surface area of 4 pi r squared. And that's the area over which we'll distribute all of the sun's energy. And the larger the sphere is, the more surface area over which you spread that out. And so it's not nearly as intense out in Jupiter because this is a much larger surface area than is over this tiny surface area on Mercury. So much, much denser packed photons hitting you here and frying you, versus over here you might not even feel warm. Here's our relationship for intensity then. We had come up with this idea looking at our graph of it that it might be a 1/r² relationship, and sure enough, that's what our theory came out. And I'm going to use a P here for power. And the power we're going to use is and this isn't technically a power unit, but we're going to use lumens. But I could use the total energy emitted from the sun in terms of its radiance, the radiant energy per unit time, and get power units, or watts, joules per second, or watts, and plug it in here. So we could use this intensity equation for a variety of different forms. And we're going to use it for our luminosity instead. So we're going to use lumens per meter squared. When we're trying to fit a curve, don't use dot to dots, don't connect your points. You might use a French curve or something to try to do a curve fit, but really, we only want to do a curve fit if we actually have a way of finding the equation for the curve. So for example, using regression. And in this case, what we're going to do is we're going to use not a regression, but we're going to use our linearization process. And the equation that we're going to look at is we're going to try to factor out this 1/r² term out of our equation. So we can take this data and transition over to a linear set of data that then you can draw your line of best fit through and figure out your slope and work out the values. So let's linearize this data. Well, first of all, we need to know from theory, or guess at the mathematical function, which we have already done, and we found out this is our equation. It's power divided by unit area, and instead of power, we actually use luminance here. And our next step in the process was to factor out our independent variable. And here's the independent variable with the square. We want to factor that out to the right. And as you would agree, I think we have 1/r² that can factor out of this. If we multiply this back together, we'd find this again. All right. So we are going to, instead of plot a 1/r² function, we're going to actually take this and do a u substitution and treat this whole chunk here as our new variable. For example, if this was an x, we'd have a y equals k times x. And does this look like y equals k times x? Yes, it does. All right, our k, our constant of proportionality, or our slope, is going to be our intensity in lumens over 4 pi. And our new independent variable we're going to use to represent our x is going to be 1/r². So we're going to create a 1/r² axis to plot against rather than a r axis. All right, so the next step is to take our set of data, and remember our set of data, we really want to do this in meters and in lux, lumens per meter squared. So we're going to add a brand new column for our data, and the new column we're going to call, this is our new x value, our new independent variable, is going to be 1/r². All right, and so the next step is to calculate a brand new set of values by basically taking my r values here and doing this little bit of math, 1 over r squared in each case. And here's the first few examples that I've done using centimeters and foot candles, centimeters in this case. But remember that you'd want to do this in meters squared, not centimeters squared. And then you need to take this new value for your x-axis and plot it against your output values, your y values. All right. And remember, if you already have a graph of this as a curve, which you do, and I want you to use that one, you can use the same exact x-axis that you have down below and just draw a brand new one down below and call it 1 over r squared. Use the same values and plot these values. You may find, though, that the scale of these numbers, I don't know, take a look at the scale of the numbers, and you'll see that these numbers vary from 0 over to 0.04 using my centimeter values. So you may want to reshift the scale out on that a little bit and redraw the graph a little bit. Use your judgment on that. And as you can see, once we do that, the data looks like it's quite linear. And so the next step is to take that nice linearized data and we draw a line of best fit through that data, and you're going to work out your equation for this. Okay? And so I've hidden what my solution is. And my solution wouldn't be very valuable to in any case since it was using the crappy units. So next step is, once you come up with your equation for this, write down the line of best fit equation that you came up with and write down the theoretical equation that we started with. So you're going to have your numbers in here. You're going to have I equals some slope times 1 over r squared here. That's our linearized variable that we used. And how do these things relate to each other? Well, that slope that you found is going to equal p over 4 pi. And so what you need to do is set your slope, whatever that value is, equal to p over 4 pi, and solve for p just by multiplying both sides of your equation by 4 pi. And voila, you have your power, which was really luminosity, in lumens to solve the problem. So that is your answer, and that will help you find what value of light bulb that we used in this experiment.